Okay. So let's go ahead and get this. So, as I mentioned, sent out the emails and stuff like that. This is going to be sort of aimed at being a two-parter today and also tomorrow. And then Wednesday, I will do what I can to review both. But obviously, there's not going to be a whole lot of time to go too in-depth with everything. So that will be meant more as sort of, for those of you who are here for all three, which I know is actually the vast majority of you, then Wednesday should be kind of a culmination of everything. So, we'll sort of grind through a few details here, not too much, because I want to emphasize problem solving. But after we've done that today, and then tomorrow prepping for exam 2 and things like that, Wednesday will be kind of a broader overview, hopefully sort of smoothing out any rough areas and answering any final questions for you. All right, so today we'll be primarily solving problems up to exam 1, although I am not going to go into energy and work and stuff like that. So we'll be going through essentially, the basic stuff. Again, making sure that everyone's totally clear on all the definitions, on the vector analysis, and all that stuff. It shouldn't take too long. And then we'll actually start getting into some physics when we start talking about one-dimensional motion, when we start talking about projectiles, when we start talking about circular motion, when we start doing all that kind of thing. But we will end just before the energy unit, and then tomorrow we're going to start with energy, then conservation of momentum, and then we'll get into rotational motion and things like that for exam 2. Okay? So, before I get started doing physics, I wanted to outline for you kind of the way that I solve problems. So, that's actually the hardest part of teaching from the perspective of your professors, is crystallizing how they think of a problem in terms of like a set of steps for a student to use, because we don't think of it that way. It's not a set of steps. It's not a procedure that we go through. It's just sort of seeing a problem and attacking it a number of different ways until we find a solution. But that's not particularly helpful when you're trying to solve exam problems. So I'm going to write this in sort of a box about right here, and I'm going to keep it. And so when we go through and we do example problems, I'm going to keep referring back to this part. So the first step that I would like to address, I'm going to call A, is comprehend the problem. These are going to seem too simple. Okay, they're going to seem obvious, but as you'll see, hopefully, when we start doing example problems, there is subtlety involved in comprehending exactly what the problem is asking. By comprehension of the problem, what I mean is, number one, what are you being asked? Which is to say, what are you asked to then provide? What are you supposed to write down and put in a box for us to grade? Is it a particular quantity? Like, is it a value for a normal force, or is it a value for a coefficient of friction or something like that? Or is it a condition, for example, that the normal force has to be greater than this, or that the mass should be smaller than that, or the frequency should be larger, or something like that. And can you create a mental picture of the problem? Not the problem, really, but can you create a mental picture of the system so that you can at least sort of envision where the solution that you're trying to search for fits in with everything else? After you've comprehended the problem, now you need to comprehend the system. By that I mean, do you really know what you're talking about? Like, do you know, if you have a mass and spring system, do you really understand how you have a wall and maybe a spring attached to it and a mass in the end? Can you envision it bouncing back and forth? That would be an example. A projectile, can you imagine it being shot out? Can you visualize in your head a cannonball sailing across the landscape and then landing some other distance away? Things like that. Okay? So that's what I mean by comprehension of the system. In terms of how to comprehend the system, one of the most important things you can do that is hugely neglected by almost everybody is draw a picture, a big picture. Okay, don't draw a tiny thing where all the labels get mixed up and you can't really read what you wrote. Take all the space you want, draw a huge picture of the thing that you're trying to understand in diagram. Because you'd be amazed actually sometimes how just seeing the way particular lines intersect or the way particular arrows point against one another can actually lead you to a solution. So drawing pictures like that. You also need to understand which laws or rules or principles govern the behavior of the system. So is this a system that obeys conservation of energy? Does it obey conservation of momentum? Should I try and think of this like a sort of a work-energy sort of relationship, or should I think of it like a projectile problem or 1D motion or whatever? Right? So you need to understand and be able to connect the question that you're being asked with the laws that govern the behavior of the system, as well as any kind of additional constraints. Right? For example, if you had a mass on an incline and one of the constraints was the mass is not moving, so the coefficient of friction is large enough that the thing doesn't move. Do you really understand what that means when the coefficient is so large that no acceleration starts? Things like that. So those are the additional conditions specified in the problem. Part C would be find a route to the solution. And I don't mean write down a bunch of formulas and try and see what comes out, right? How can I combine these variables in order to get something that looks kind of like a length, which is basically what I'm being asked for? No. So what we'll be trying to do is trying to see, forget math, forget any of that stuff. Can you understand and see how the laws that govern the behavior of the system connect the information that you're given at the beginning to the solution that you're trying to find at the end? Okay? That'll become a little bit more clear when we start doing problems. So this part C is the most important part, right? Well, I mean, I guess it's all kind of cumulatively important, but this is the hardest part, is once you understand kind of how the system works and the rules that govern it, can you find a route to this solution? Okay. And once you sort of planned out a pathway, but have not yet solved the problem, then you have to crank out the algebra. Right? So that's part D, which is just algebra. In principle, this is the easiest part. Okay? Because you're done now. All you have to do is that robotic, divide by the multiplier, subtract, solve for x, that kind of thing. Right? So this is where the physics is, and this is where the math is. Okay? All right. So that's kind of the procedure that we'll be going to try to emulate when we solve all these problems. Now, some of the early problems, they'll be so trivial and basic that it would be kind of, a waste of time to break it down into every one of these things like that. Like when you're breaking a vector into components, for example, you wouldn't, because it's not really a physics problem. But when we start to get into more physics problems, for example, when we start to do projectile motion and things like that, I'll try to relate the way I solve the problem to this as a general procedure. So, just as a really quick overview of absolutely everything. Vectors and components. So you're exposed to three types of mathematical structure in this course. Okay. The first is you had bare numbers. You may not have called them that, but that's what I call them, bare numbers. For example, 2 or 5.7 or negative 9.8. Those are bare numbers. You also had scalar quantities, scalars, which include 6.7 meters, 25 seconds, or 30 kilograms. These are bare numbers with units attached. Another often neglected thing, and especially in intro classes, but even all the way up, is an understanding of how these units play a role. Right? If I'm asking for a length, and you're giving me variables, right, if we're not plugging in numbers, if I'm asking for a length, and you give me something that is a mass divided by time, and there's no length in there, right? So understanding how these things combine with each other, and understanding that, you know, meters don't just evaporate, that they have to cancel with other units and composite units and things like that, which I'm not going to go over. But that should be something that factors into your understanding. So, you know, if you just don't know and you just are writing down a number, then fine. But if you are really trying to make sure that your solution is correct, and you check the units of the thing, and they're not right, then obviously you have to go back and find something. So, understanding the difference between these two things, it seems, again, like I'm being kind of patronizing and I'm, you know, going over basic itty-bitty steps, but it's amazingly useful to understand the difference between those two things. And lastly, you have vectors. Right? Vectors are scalars, but with an orientation attached. So, for example, 2 meters that way is not the same as 2 meters this way. 2 meters is 2 meters, but they're pointed in different directions. So there are all kinds of geometrical ways to add vectors together. You can add, you know, the tip of one to the tail of the other. You can use the parallelogram rule or whatever you feel like doing. But as you quickly became aware when you did this the first time around, adding arrows together is, number one, cumbersome, and number two, very, very, very inefficient when you're trying to do things on a more theoretical level, right? So instead, we started to break them up into components. The way we need to do that is if we have a vector, which I'm going to call A like this, to resolve this into components, we need to give it some kind of coordinate system. So I'll just make a coordinate system like this. X points this way, and Y points this way. As soon as I define that coordinate system, I have now overlaid a grid on this board that I'm working on. Okay? And I need to resolve this into components like this. So A has an X component, AX, and a Y component, AY. And if the thing is inclined at an angle, so I'll call theta, then AX is equal to the magnitude of A, the length of A, times the cosine of that angle theta, and AY is the magnitude of the vector A times the sine of that angle theta. All that is boring and we know how to do all that stuff. But what I want you to be able to do, and be sure that you understand how to do, is to do this when it's not that pretty. So, for example, I have a vector that looks like this, and I'm calling this my y-axis, and I'm calling this my x-axis. Can you break that vector into components if I give you the angle? So, here's the vector, so I could say, all right, well, here's my x direction, here's my y direction, here's some angle of inclination, theta of some kind. Can you now break that into components? Because it's not right like this, right? Normally we're used to saying, okay, sine theta is the thing that goes like this, and cosine theta is the thing that goes like that. But if it's at a weird angle or something, as these problems tend to be, for example, when you have an incline, if you recall, when we had to break that up into components, it's not nice and simple like this. So when we do it like this, what you really should understand is that the cosine goes with the side that is adjacent to the angle. So this guy is the cosine, and this guy is the sine. Adjacent meaning lying right next to. So whichever side, so you have the hypotenuse, which is the length of the whole vector, and whichever side is right next to the angle that is not the hypotenuse, so this guy is the cosine, and the opposite one is the sine. So anytime you have that angle, don't think of it like the y component is sine, the x component is cosine, because there are plenty of systems where it's going to be reversed. So you should really think cosine is the adjacent one, sine is cosine is the adjacent one, sine is the opposite one. Okay? So just so we understand how to break those things up. Okay. So, you know, we do need to move kind of fast, but does anybody have anything about this? This should be pretty old hat for almost everybody, but just, you know, to clarify and make sure that we're all good. Yes. All right. I'm not going to do any problems with that because it's a little bit too basic. But, you know, in the problems that come up, we're going to have to be able to do that. Okay. So, in physics, the quantities of interest that we like to talk about are the position, the velocity, and the acceleration. We have, as you know, a huge tendency to overuse variables in physics. We overload them, which means that they have multiple definitions, and the definition that we're using depends on context. I noticed this last time, and I again apologize to both my my Wednesday and my Thursday, and to, again, I'll apologize again to my Fridays, right, for you guys, the ones that caught it, really. In our discussion session this week, I used the variable omega for two completely different quantities, right one after the other. Right? So it wasn't at literally the same time, but it was an example, moving on to a different example, where that variable omega was used for two completely different quantities. Okay? I've planned these out a little bit more, so I've made sure that I'm not going to overload variables that way. But you need to be prepared for the possibility that, unfortunately, we only have so many, 26 Latin letters, however many Greek letters are, 27. However many, Greek letters we have as well, but we really kind of start running out. And in undergrad, you don't like to use Greek letters because people think it looks scary, so it gets tough, and a lot of the time you overload variables. So what I'm going to do is, instead of writing v for velocity, whenever I can, I'm going to use the dot notation, meaning time derivative. Okay? So the vector r, which has components, which is a function of time, and has components x of t, y of t, and z of t. Actually, you know what? Let's just do x and y, because we'll never use three components. X and y. Okay, so we'll just imagine a thing moving out on the plane somewhere. The velocity, which I normally would write like this, I'm now switching notation and writing like this. Okay, a big dot over top. R dot. Okay, that is the time derivative. Is everybody good with that notation, the dot notation? So if I have a dot, what that really means is this. Okay, but this is a pain in the butt to write, so the dot. Okay, and so this is then going to be written as x dot of t and y dot of t. Okay, and lastly we have our acceleration, which is our double dot, so two dots above t, and that is x and y. Okay. One other added advantage. Now, this has, upsides and downsides to using notation like that, right? Upside, well, first we'll start with the downside. It looks kind of cluttered, right? It's a little bit confusing sometimes, and it's easier to see the distinction between things when they're used, when there are completely different symbols that are used rather than just slightly modified symbols. But that's also the downside, that a lot of times when we talk about velocity and we use the symbol v or v sub x, we kind of forget that it's so intimately connected with the variable x. Okay. So this way to do it is, sort of a double-edged sword, but that's the way we're going to do it to try and avoid overload it. So I'm going to try and use as few symbols as possible as we go through here. Okay? So we'll start off with just 1D motion. Okay? So one-dimensional motion. And we'll start off with a constant acceleration. So let's just say that a of t, right, no vectors anymore because we're just moving along a line. So whenever you do this, what I want you to think about is the origin of the chalk tray is right here. Positive is that way, negative is that way. So anytime I talk about a position or acceleration or velocity, it's along the chalk tray. Okay? All right, so a of t is just the constant a. All right? If that's the case, what can I do? Well, this a of t is really saying that x double dot of t is equal to a. And so we just take an antiderivative to get back to the velocity. So the velocity x dot of t is equal to a times t plus a constant, right? And for fairly obvious reasons, we're going to call that constant v naught. Right? Because if you plug in t equals 0, this term goes away, and you find that the velocity at time t equals 0 is v naught. So v naught is our initial velocity, or our velocity at time 0. a times t squared plus v naught times t plus, for exactly the same reason, x naught. Notice that this x naught and this v naught are just integration constants. Okay, so I need to specify these really to be able to know how the solution is really going to go. Right? Normally this is written in a slightly different form. Typically you have either this or x of t, not a different form, just a different order, is equal to x naught plus v naught times t plus 1/2 times a times t squared. Or you also have this. Delta x is equal to v naught times t plus 1/2 a t squared, where delta x is just x minus x naught. Right? So this is the most general possible case where you're assuming that the object or particle or whatever you're thinking of can be starting from any point along the line. So you say, all right, I define this to be 0, but at time 0, the eraser happens to be, over here at x equals, 50 centimeters or something like that. That would be x naught. But if really all you care about is during the trajectory of the thing, or from the time t equals 0 to whenever, how far does it move, relative to where it started, then delta x is the way to go. Normally speaking, this is how I do it, but it's sometimes a little bit more enlightening to use the first form. So either one is fine. Okay. All right. We can also cast this in a slightly different form, but I'm going to do that in just a second. So first, let's do an example problem. Okay. So, example. First, let me get a couple different markers here. Okay, so example in blue. Right, so if I have my eraser that starts here, I want to know how far it will have gone under these conditions. The acceleration that it experiences is equal to 10 meters per second squared. And it's positive acceleration, so it's accelerating in that direction. Its initial speed, it begins with v naught equals 5 meters per second. And I want to know how fast or how far it's gone after t equals 2 seconds. Okay, so I say, all right, well, I understand the problem. What am I being asked for? I'm being asked for delta x. Displacement of the thing. Right? The system, it's fine. Constant acceleration, one-dimensional motion. So find the root to the solution. There is no root to the solution. It's just plug it into the equation that we know and we understand, right? So we associate this equation with one-dimensional motion under the influence of constant acceleration, right? And so we just plug it in. So delta x is equal to 5 times 2, that's v naught times t, plus 1/2 times 10 times 4. Okay. So what's that? 20 plus 10 is 30 meters. And we're done. Right? So that wasn't much of an exercise in physics. That was really kind of just plugging it into the equation that we already know. But it's a start. So that's example number 1. Let me ask you example number 2. Slightly different question. Right? So I'm saying over a time interval, over a certain amount of time, the displacement of the particle from its original place is negative 20 meters, which just means 20 meters backwards. So if it starts here, then it ends up, after some amount of time that I haven't yet specified, being 20 meters the other direction. It starts off at rest, so its initial velocity is equal to 0, and its acceleration, a, is equal to minus 10 meters per second squared. Okay. So I want to know how long did it take. So now, again, comprehend the problem. Same stuff, right? Same thing, same system, same equations that govern it, but now we have a different variable that we're looking for, right? We know how to solve for delta x, we just plug it in. But now we got to try to solve for t, right? So we got to think that everything in here is known except for t. It may be useful for those of you who find it really difficult to manipulate variables. Like, I know that there's a bit of a learning curve, and there are some people that still aren't really comfortable without plugging numbers into everything all the time. And so you can either, although I really hesitate to advise you to just plug in numbers, right? Because the variables are immensely useful in telling you when your solution makes any kind of sense or not. But if it makes you feel better, you can just look, okay, delta x equals minus 20, so you plug in minus 20. B naught equals 0, you plug in 0. A equals minus 10, right? Or you can look for, which variables you know and which ones you don't know, right? So in this equation, the only thing we don't know is t. So let's go with the thing that I advised you not to do, because this is a simple enough problem that it kind of calls for it. So we say, all right, delta x is equal to minus 20 meters. The initial velocity is 0, so this term goes away completely, and I'm left with 1/2 times minus 10 times t squared, right? And so it follows that t squared is going to equal 4, and t is equal to 2 seconds. Okay? And that's just the solving. Now, you'll also notice, by the way, that when I'm doing these examples, I don't write units here, but I do write them at the end. Okay? So from a practical, points point of view, right, you need to have units attached to your answers, or you're going to get points docked. It's extremely important to know what you're talking about. The other thing is, the unit, it would essentially be an exercise in just keeping track of units if I wrote them all in here. So, for example, t squared is really 4 seconds squared. And you might say, what is a second squared? It's not a physical unit. It doesn't have any particular meaning. It's just the square of something that has units, seconds. What you do need to be careful of, though, is if you take this approach where you just write down the bare numbers and just sort of let the units slide for a little bit, that you're using consistent units, right? Which almost always means meters, kilograms, seconds. That's it, right? Those translate into newtons and joules and stuff like that. But if at any point you have centimeters or nanometers or microseconds or tons or pounds or something like that, you need to do these conversions first. I'm not going to go over conversions, but you need to do the unit conversions to get it into those nice natural base SI units so that you can freely throw the units away and just work with bare numbers here. It's a dangerous prescription if you're not being consistent with the units. All right, so that's it. But I said earlier that it would be a good idea to be able to solve for variables. So I might say, all right, let me take that problem that I just did with the time and do everything but not plug numbers in, right? I'll plug this in because otherwise it's going to be kind of ugly. But other than that, so I say, all right, doing this in terms of just finding the variable, or the analytic solution or the symbolic solution, is done like this. So you say, all right, delta x is equal to 1/2 a times t squared. Fair enough. Solve, and you can see that t squared is equal to 2 delta x divided by a, which means that t is equal to the square root of 2 delta x divided by a. And now you say, okay, delta x is negative 20, a is negative 10, so delta x over a is 2. 2 times 2 is 4, the square root of 4 equals 2. And so this is the way that, in general, I would prefer you do it if it were up to me, which it's not, right? But if it was, I would prefer you do it this way first, for a number of reasons, right? One of which being, if you just write down 2 seconds, or if you just write down 3.5 seconds, and it's not right, there's nothing that we can do to give you credit for it. We would love to, really, I swear. But if it's just not right and there's no rationale behind it, or the rationale is impossible for us to follow, so you need to lay a trail of breadcrumbs to help us along. You can imagine, right, if you had to look through someone else's exam and try and follow their logic, how would you want them to sort of lay it out for you? So this is better in that sense, that this gives us an idea of what kind of logic that you were following. And secondly, if I had this as an answer, right, if I just somehow drop the A in there, this does not have units of time, so that doesn't make any sense. Right? So if you're inclined towards dimensional analysis, you would recognize that 2x, that delta x over A has units of length, or meters, over meters per second squared. The meters cancel, second squared goes on top, and you have units of time. Okay, so multiple reasons symbolic stuff is, when possible, to be favored. Okay. We know how to do all that stuff, so let's get to something slightly meatier. Okay. Quickly, let's cast this into a slightly different form. So when I say cast this into a different form, I say, all right, well, if it's moving under the influence of constant acceleration, I might know the time and the initial velocity and acceleration, but I also might know something about the final velocity. And I know that the final velocity, v final, is equal to the initial velocity, v naught, plus the acceleration times the time. Which means that the time is equal to v final minus v naught divided by A. And so I can plug this into this equation for t. So I can replace t with this. And what you will find, if you haven't done it or you're not familiar with it, you don't really remember, then just do it. It's a simple algebraic exercise. And what you get is that v final squared minus v initial squared, v final squared equals v initial squared plus 2a delta x. Okay? So this is the other equation that governs one-dimensional motion. Notice that I just derived one from the other, and I could have started here and gone backwards using this and found out that one, right? They're basically the same thing. But they just rely on slightly different information. So any problem that can be solved with one can be solved with the other. You just might have to go through an extra step. So the classic example is you have a plane that is on a runway, okay? And a runway, plane on a runway. Right? So the length of the runway is going to be 1,000 meters. Okay? And in order to take off, the plane has to reach, must reach 20 meters per second. Right? Otherwise, it's going to run off the end of the runway. So the question is then, what must its acceleration be in order for this to work? So you have a kilometer-long runway, and you have to get 20 meters per second. So what do you do? Right? And this is a straightforward application of this formula, where I would simply put v initial being 0, because we assume that the plane is starting from rest and you're ready to go. The acceleration we don't know, so we leave it as a. Delta x would be 1,000, right? And v final is 20 meters per second. And so you solve for this, and what you would find if you did this is that a is equal to 0.2 meters per second squared. Very modest acceleration. Very long runway, not very fast. Okay? So that's literally plugging numbers into here again. But recognize that you could also use this equation. Right? You wouldn't know what t is, but you do know what v final is. So you could relate v final to the acceleration of the time and all that stuff. So you could use the same stuff, but this one is more convenient for this. So you should remember both and understand when you should apply one or the other. This one is when you know the time, and this one's when you don't. Okay? But they can be used to solve exactly the same kind of problem. Okay. One-dimensional motion is boring, so we're done with that now, unless you have any questions for me about any of that stuff, either of those two equations that we did, because I would like to now go on. Yeah?
How do you get to the VF squared, VO squared?
This one?
Yeah.
So if I plug this in for time here and here, right, and I work through some algebra, 2 or 3 lines of algebra, I will arrive at this equation. Right? So you can remember it if you like, but it's a useful exercise to be able to derive this formula from this one. Okay? So again, again, just remembering that the definition of the final velocity is the initial velocity plus the acceleration times whatever time, solving for t, plugging back in here, and now you've expressed it in a way that doesn't explicitly require you to know what length of time your thing's been moving. Okay? Anything else? Okay, so let's get on to projectiles. By the way, you know, for those of you who feel that some of this stuff is a little bit too basic, or you're feeling kind of bored or whatever like that, try and look at it from a different perspective. Try and look at it through a new lens. Because I guarantee you that you're not as good at it now as you're going to be eventually. So try and see through the problems I'm about to do as an example. Try and see through it before I'm done, before I've finished writing, right? Don't think of it in terms of what's the algebraic thing, but think of it like, you know, for example, the range of the particle, the angular dependence of the range, right? Think about why. Physically, there should be a sine of 2 theta in there, or a sine times a cosine, right? We'll get to that in a minute, but again, it's something to think about. So if you're bored, then try and go a little bit ahead. Okay. So, this is the simplest. So a projectile problem is a problem also called a free fall problem, where you have now 2 components, right? So you look at the x component and the y component, and they happen to be completely decoupled, which means that if you remember, I said that the one-dimensional motion is like motion along this tray. What it really is it's motion along 2 trays. That's all, right? So you don't have to think of it like x and y, the thing moving in a plane. You can think of it like motion along this one and simultaneously motion along a different, a chalk tray that was vertical, for example. So it doesn't have to correspond to a physical or a single particle or a point moving across a plane, because the beauty of this and the reason that this is nice and simple is because the x equation and the y equation have absolutely nothing to do with one another unless I force them to, which you do during the projectile problems. And I'll show you what I mean right now. So the most general form that you can write this is delta x is equal to v x naught times t, and that's it. And delta y is equal to vy naught times t minus 1/2 g t squared. Right? Both of these are examples of that one-dimensional motion equation that we used not too long ago, except in the case of the x direction, there is no acceleration in the x direction, so we plug in a equals 0. And in the y direction, the acceleration is the acceleration due to gravity, which is minus g here. It's also worth noting that in my universe, for those of you who are not in my discussion section, I know there are several of you guys, in my universe, g is 10 always, or minus 10. I don't use 9.8 when I'm doing examples on the board because there's no functional difference between the two, unless you're just being picky about decimal points, and it lets me multiply. Okay? So, that's where we start. I'm going to change this slightly because I'm going to assume that we're going to break up the components of the initial velocity, and I'm going to say that delta x is equal to v naught times t times cosine of the angle of inclination, cosine of the angle at which the thing is fired. And delta y is going to be v naught times t times sine of the angle. Show that. Okay. Okay, so the first question that I have for you is, if I just shoot, minus 1/2 gt squared. Right, so these are the 2 equations that govern all projectile motion. So if you have a problem with a projectile in it, that's where you need to start. Okay, so angle v naught. Okay, so my question for you is, how long will this thing be in the air? Right? How long until it comes back down and stops? And then it'll stop probably, based on what I drew, about here. And that's where I'm assuming it's going to hit. So, question number 1, how long is it going to be in the air? comprehend the problem. Free fall. Not too difficult, right? Comprehend the system. These are the equations that govern it, right? If we know the initial velocity. So, here's the tough part then for this problem. And it's not tough if you remember how to do it. But if you've never done it before, or if you kind of forget, how do we find how long the thing's in the air? Well, the first thing we need to do is we need to define what it means to say the thing has landed. Right? What am I talking about quantitatively when I ask, what does it mean for the thing to have landed? How do I define the end of the trajectory? And the definition is when it comes back to the same height that it started at. Right? When it's here, it goes up, and then when it comes back down and it's reached the same height as it was initially, then it's done, then it's over. Right? So really saying how long is it in the air, what I'm really asking is, when is delta y equal to 0? Right? And that is a way easier question to immediately answer than, how long is it in the air? Because how long is it in the air is the physical question. But you need to cast it in mathematical form, which is this. And from there, all we have to do is solve. So we say, all right, delta y is 0. So that means that 0 is equal to v naught times t times sine theta minus 1/2 gt squared. Or, to put it a slightly different way, we have an equality like that. Right? If this is true, then delta y is equal to 0. And there are two solutions to this problem. The first is when t is equal to 0. And that's fairly obvious, right? It hasn't moved because it hasn't started yet. At time t equals 0, delta y is equal to 0. But there's another place. Divide by t. I get this. And then I multiply and divide, and I find that t is equal to 2 v naught sine theta divided by g. Cool. And I'm going to put a little star on this, or yeah, put a little star. Right. And this is, the star means the final time, right? The time at the end of the trajectory. Right. So we've arrived here. Cool. Why is it a sine? Why is it not a cosine? Why could it physically not be a cosine? But you don't have to answer, just think. What is it about the sine? So when theta is small, sine theta is small. When theta is close to 90 degrees, sine theta is close to 1. So the best we can do is to make this 1, which is shooting it straight up, which of course is going to be the longest amount of time that it's in, right? We throw it straight up. If we throw it at the same speed at any other angle, it's going to hit first. So that makes sense, all right? So you try and get some, even though it seems like a trivial example, try and put some physicality behind it. Cool. So that's question number 1. Question number 2. How far does it go? Right? So what is this distance that it has traveled in this time? Notice that this has absolutely nothing to do whatsoever with the x equation of motion. Right? The x equation of motion for this guy, or this one, right, has not had any input yet. But now it will, because now we say how far in the x direction has it traveled by the time it hits the ground. So really what we're doing is we're saying, all right, when it hits the ground, that means it's stopped. So my question is, when does it hit the ground? So I set delta y equal to 0. I find my t. This t star is the time it takes for it to go up and then back down again, and it will land here. So in that time, how far has it gone? Easy. If I call that distance r for range, okay, I'll just write the word range is equal to v naught times t times cosine theta. But t is this. Okay? And if I multiply that out, what I get is 2 v naught sine theta, 2 v naught squared sine theta cosine theta divided by 8. Okay? And for those of you who are savvy with trigonometric identities, that is v naught squared sine of 2 theta divided by 8. There's 2 sine cosine is equal to sine. So I'm not going to address this in any length and detail, but why is it a sine 2 theta? Why not sine theta? Why couldn't it physically be cosine theta? Why is there a sine and a cosine? Okay. Because cosine dies at 90 degrees, but sine dies at 0, so they're like competing, right? So there's a competition between sine and cosine. Physically, what is that? Physically, I'm sorry?
45 degrees.
Yeah, so the maximum you're going to get is 45 degrees. It's kind of when, you know, when they're going to fight, and the best you'll ever do is when you're at 45 degrees and they're the same, right? So do you remember, any of you guys that are in my sections in particular, do any of you guys remember what I said was physically the reason that you had this fight between the sine and the cosine? The physical reason you have that fight is because there's a battle between how fast is it moving in this direction versus how long has it stayed in the air, right? If you shoot it straight up, it stays in the air for a very long time, but it's not moving in this direction hardly at all, right? And so the range is small. Likewise, if I shoot it at an angle that's just above horizontal, it's going very fast this way, but it's only in the air for a very short amount of time. And so again, the range is small. And so that competition is reflected in the sine times the cosine, which you can combine into the sine of 2 theta. Okay? So again, something to put a little bit of physicality behind some of the more abstract math. Okay? All right. So I have one projectile motion example, and then we'll move on to circles. Okay, so projectile motion example. Okay, so as it turns out, I am desperately in love with a lady, but the family doesn't like me very much. So when we communicate, we have to communicate via catapult. You don't know my life. All right, no, this is serious business. This is some serious shit. All right. Okay. So here's the idea. So I need to shoot a projectile up to this girl's window. And I don't know what it is. What is it? What projectile do I need to deliver?
A love letter.
Love letter.
I feel like I would require a catapult for love letter, but all right, yeah. A love letter connected to a rock. This is her dad's window. Oh shit. Okay, this is her dad's window, and I want to hit it, right? So here's the window right here, and I want to just break it. So I'm going to come in here, and I want it to hit like directly going in. So I don't want any glancing shots, right? So I'm trying to shatter this thing. So I want the momentum of my rock to be breaking right through. Okay? Now, I'm not a particularly good engineer yet, right? So I'm only able to shoot this at one speed, and I can use the velocity v naught is equal to 20 meters per second. That's the best I can do. I can't tune it at all. Right? But I can change whatever, I can put whatever angle I like. He lives in kind of like a high-rise thing, so this is going to be 10 meters that he lives around. All right. So my question is the following. Number one, how far away and at what angle should I shoot this thing at 20 meters per second, such that it hits, number one, it hits his window, and number two, it hits it dead on, right? So it's not glancing up. This is not an immediately obvious problem, right? There's some subtlety to this. So, what do I do? So, yeah. So that's an excellent first thing, right? So first thing, let's go back to this real quick, because again, I just try to feed into this over and over again. Comprehending the problem. Again, it's a projectile motion equation. So comprehend the problem and comprehend the system are kind of tied together. I understand that the equations that govern the motion of this thing are these, and that's basically it. I don't really need to do anything else. But in comprehend the system or comprehend the problem, one of those, I mentioned external constraints, right? What constraints am I placing on the problem? And I'm putting two constraints on the problem. Constraint number one, in red, constraint one, delta y is equal to 10, right, meters. So that's the first condition. Okay. Delta y has to equal 10. And what's my second? Constraint 2. Okay, yes, so that's true. Yeah, so I'm going to leave that just as this here. So these constraints, what I mean by constraints are like solution conditions, right? The conditions on my answer. Yeah.
If you're going directly horizontal, then you have to not have any vertical motion.
That's absolutely beautiful, right? So my vertical velocity, or my y component of my velocity, must be 0. So that means that y dot is equal to 0. Right? And what is y dot, by the way? It's just y dot is equal to the initial velocity, which is v naught sine theta minus g times t. Nice. Great. So those are my two conditions. But look, so I'm assuming, right, that there's going to be some time t at which I have gone some distance like this, and it's hit the window and it's broken, right? So finding t would be really the thing I need to do. And you can see that here, I've already done it, right? So by being able to quantify the condition that it hits dead on, which is to say it doesn't glance off, quantitatively what that means is the y component of the velocity is 0. And so what that further means is that this is equal to 0, and I find that t star, which is the time of impact, is going to be equal to v naught sine theta divided by g. And if I plug in the values that I had before, v naught was 20, g is 10, which means I am at 2 times sine theta. Right? Remember again that I'm completely neglecting units, but I'm being good. I'm using everything in meters and seconds and kilograms. Yeah?
Doesn't it matter how close and how far away you are from that?
Yeah, so that was the second part of the problem, right?
Oh.
So not only at what angle should I shoot it, but where should I shoot it? But hopefully we can find that out in a second. Regardless of where I am, I know that this part has to be true, right? Because it's got to hit dead on. So I found the time. The time is 2 times sine theta in appropriate units, which would be seconds. Okay? So I found this. That's from constraint number 1. How about constraint number 2? What does that tell me? I'm sorry, constraint number, whatever I just said. I solved constraint number 2. How about constraint number 1? Delta y equals 10. So, yeah.
Wasn't the final time 2 be not sine theta?
That was for an average, that was for, remember, when it was fired up and then it came back down to the same level. Right? It's not at the same level now. Right? So that equation that we did before was not part of this problem. Still a projectile problem. But in that case, I defined the end of the trajectory to be when it had reached the same level. Now I've defined the end of the trajectory to be when it's equal, when it's gone up by 10. Right? Or equivalently by when it doesn't have a horizontal component velocity. Okay, so that makes sense? Yeah. Also, this is 2 v naught sine theta of g. This is, as you can see, half, right, of the full answer, which is because if you look at it, the trajectory of a projectile, right, that 2 v naught sine theta is the time to get to here. But I don't want that. I want the time to get to here. Right? So it's half. So you can think of it that way as well. Okay? But regardless, however we go about it, we found the time, it's equal to that. We don't know theta yet, but it's okay. We'll keep working and we'll see if we can find it. So, how about this guy now? So delta y is equal to 10 from that condition, right? Which is equal to v naught times t, 20 times 2 sine theta. So that's 40, there's another sign here, so sine squared theta minus 1/2 times g, which is 10, times 4 sine squared theta. That's it. So that's equal to 40, and then this is 20. So 20 sine squared theta. So apparently sine squared theta is equal to 1/2. Sine theta is equal to 1 over the square root of 2. And theta is equal to 45 degrees. Great. So I didn't want to know the time. I wanted to know the angle and the range. But I found the time first because it's kind of an intermediate step. And now look, I found the angle. Can I find the range now? Can I find where I should have placed it? Sure. Because I know the time, and I also know delta x, right? So the range, I mean, make that over, put that there. So the range is equal to v naught, that's 20, times t. So that's 20 times 2 times sine theta, but we just said sine theta is 1 over the square root of 2. Times cosine theta, which is also 1 over the square root of 2. So that's equal to 20 meters. Okay. So that's our mildly involved, but still relevant, I think, projectile motion example. So again, let me go back through that and cast it in this. So comprehend the problem. Projectile motion governed by these, but also having these constraints, right? This is the most important part, is quantifying this. Okay? So the insight that delta y had to equal 10 and that y dot had to equal 0 at the time of impact was crucial. Right? Once we came across those, all we did was solve for stuff. Right? We're just solving algebraic equations, plugging them into other equations, and finding the variables that are relevant, that we were looking for. So the physics was here. And this was algebra. So comprehend the problem and comprehend the system was understand that these equations are to be used and that these constraints are the things that we need to take into account. Finding a route to the solution, we just sort of plug stuff in. Perfectly good route to the solution. And then the algebra was cranking the rest of it out. Right? But again, that should be the easy part. Once the equation is set up, you know how to divide by constants and things. So we're good. Okay. So do you have any questions for me about the projectile equation, projectile problem? Okay. All right. So projectiles, circular motion. Okay, so this circular motion is an easy place to get tripped up, but as it turns out, it's exactly the same as one-dimensional motion, so I'm only going to do probably one example. The only thing that's different is the language, right? The words that are actually vocally being created when I talk to you about these problems are going to be different. But the math that I go through is completely identical to the one-dimensional motion problems that we've already done. Okay. So, circular motion. So, the way you begin this is by making the elementary correspondence. X of t is the same as theta of t. V, which we are now calling x dot, corresponds to theta dot, which in a previous life we called omega. But I'm going to try and avoid using that as much as possible. And similarly, our acceleration A, which we are now calling x double dot, corresponds to theta double dot, which is also known as alpha. So all of the equations that these variables. So the two equations that govern one-dimensional motion that we've used are delta x equals v naught times t plus 1/2 at squared, and also v final squared equals v naught squared plus 2a delta x. Right? So I can make a translation into the other variables, and what I get is that delta theta, the angle through which the object has turned, is equal to the initial angular velocity omega naught times t plus 1/2 times alpha, the angular acceleration, times t squared. And similarly, omega final squared equals omega naught squared plus 2 times alpha times delta theta. Okay? So in exactly the same way that these equations can be used when I ask about a particle or an eraser moving along a line, these equations are used when I ask for example, a disk that's rotating, about some kind of center. Right? So the position is analogous completely to saying, all right, well here, I'm going to pick a spot, I'm going to spray paint a dot on the edge of the thing, right? And the angle here is going to be theta. And it's going to be obviously a function of time because it's going to be changing, right? The rate at which that angle changes in radians per second, and so that's another key thing that's kind of important, is whether I use this in terms of an angular frequency or I use this in terms of an angular velocity. I'll use it in terms of an angular velocity, and I will be very explicit when I'm talking about frequencies. But in either case, the units for this are radians per second. A radian isn't really a physical unit, so if you really like to think of it, it's just inverse seconds. But that's kind of a dangerous thing because a time frequency is not the same as an angular frequency. So, f equals 1 over t is a frequency that 1 over t. Right? So this is a frequency like like sound waves or something like that in cycles per second or something like that, right? But the angular frequency is this. So just so you understand, these are related, f and omega, but just by this factor 2 pi. The point of that is not to get into it now. So I would almost rather you just whatever you wrote down, just erase it. But the point of it is that this has units of radians per second. So if it undergoes one rotation in 1 second, the angular velocity is 2 pi radians per second, 6.28 whatever radians per second. Okay, so you understand. So it's not revolutions per second, but radians per second. Okay. All right. So let's do an example here. So an example using this would be, for instance, if I had a merry-go-round, right, or some kind of rotating disc, but we'll say a merry-go-round. Okay. And let's say that it has an initial angular velocity. So initial angular velocity omega naught is equal to 0.25 radians per second. Very, very, very slow. Right? Sort of like drifting around. And I would like to get on because I like playing merry-go-rounds, but alas, it's moving and I'm safety first. Would like to get it to stop first. So I'm going to, sort of put my foot on it or put my hand on it and sort of slow it down. You know what I mean? So it's going like this slowly, but it's still turning, and I'm going to slow it down by putting my hand on it, letting it drag, and so it sort of slows to a stop, and then I can get on. Okay. So putting my hand on it, well, you could look at this later on down the line as I apply a torque to the thing, which creates an angular acceleration. But we'll get to torque tomorrow. For right now, I'm just going to say I push on it and it creates this angular acceleration alpha, which is equal to minus 0.05 radians per second squared. my first question is, how long does it take to stop? So how long does it take me, putting my hand on the thing, to slow it down from 0.25 radians per second to 0? So what do you think? Hazard a guess. 5 seconds, right? After 1 second, it's gone down by 0.05. After 2, 0.1, 0.15, 0.2. A more concrete way to say it would be omega final is equal to omega naught plus alpha times t. But omega final is equal to 0 because it's stopped. Omega naught is 0.25 plus, this is actually minus, right, because alpha is negative, minus 0.05 times t. And so solving 0.05t is equal to 0.25, and t is equal to 5 seconds. Okay. But hopefully, for a decent number of you at least, you were able to do that without thinking of it like final equals initial plus acceleration times time. This is 0, subtract, bring it together. No, it's a very simple thing, right? Every second it drops, the velocity drops by this much. So how many seconds does it have to go before this is 0? 5. Right? So that's, just to give you an idea, it seems really basic, but when you have, a lot of times you have professors, and you're going to experience this a lot as engineers, where you're going to have professors that seem like they don't know what they're talking about. They seem like they're just saying words and throwing stuff up on a board that doesn't make any sense, right? Which may be the case. But more often than not, really what it is they've gotten so used to just doing these problems that in the same way that many of you could just be like, 5 seconds. That's how they see through a problem. And so they write, oh, well this, and therefore obviously t equals 5 seconds. And then you start moving off. And a lot of people, and this happens to me all the time, is I'm just left in the dust like, oh, okay, I guess it's 5 seconds, and then moving along. So it's important that you be able to do this and sort of, from a very basic standpoint, be able to work this out. But you also want to start seeking that level of insight with problems that are more complicated than this, like the projectile problems, for example. So you can maybe see through that problem before I really started writing. So again, just things to think about. Okay, so after it's gone through that amount, so now I ask you, all right, so in those 5 seconds, through what angle has the thing turned? Okay? So for instance, if it's gone around 1 full time, then it would have gone through an angle of 2 pi radians. So it hasn't gone through 2 pi radians exactly, so I want to know how far or through what angle the thing is turned while I'm stopping it. But that's no problem, because I can use either of these equations really, because now I know every variable that's in play. But let's just use the top one. So using this equation, delta theta, which I do not know, is equal to omega naught, which is 0.25, times t, which is 5, plus, but that's really a minus, right, because alpha is negative, minus 1/2 times 0.05 times 25. And if you plug this in, assuming I know how to do algebra, this is 0.625 radians. But you can check me on that. Okay. 0.625 radians. So that's like a quarter of pi almost. Okay, so it's 8 to 2 pi, so about 22 degrees or so, 22 and a half, something like that. You do a picture in your head, right? Because you want to think all the time, what does this look like? What does this look like? What does this look like? Okay. So that's just some, non-uniform circular motion, some acceleration stuff. But as you can see, the equations that we deal with in this, final equals initial plus acceleration times time. This guy. If we had used this, which we certainly could have, right, because we knew the final velocity, which was 0, the initial, which is 0.25, alpha, which is negative 0.05, and we could have found it from there as well. But these equations for the non-uniform circular motion are identical to the equations for non-uniform motion along a line with just a translation between the variables. So I don't feel like it necessarily requires a lot more time to be spent on it, but if you feel that way, then you can certainly ask me afterwards, or you can work with a few extra problems on your own. So for the non-circular motion, are there any pressing questions to get to before we hit Newton's laws, which is really like the meat and potatoes of the last part that I want to get to? Cool. So this now. And here, when we start doing Newton's laws, now I'm going to start hitting this ABCD thing, because now it's going to start playing a role, because we're a little bit past the actual math part now, and now we're just starting to get to something that can be considered a physics problem, really. So I'm going to add to our box as well, but I'm going to do it in a different color. I'm going to do it in red. And I'm going to write down what Newton's laws actually are. Newton's laws. Number one, objects in motion. In motion, dot, dot, dot. And rest. What you really should remember is in constant in motion with, let's try it this way, objects in motion with constant velocity dot, dot, dot. Right? And objects at rest tend to, so objects in motion with constant velocity tend to stay in motion with constant velocity. Objects at rest tend to stay at rest unless actual time lasts. What does that really mean? What is the content of Newton's first law? And it sounds kind of like it's an immediate consequence of Newton's second law. So Newton's second law says to F, the sum of all the forces on a body are equal to its mass times its resulting acceleration. So you can see that if the sum of the forces on a body are 0, then the acceleration is going to be 0, which means that the velocity will be constant. It could be 0, right? Zero velocity is a constant velocity, so it could be at rest, or it could be moving in a straight line with constant speed. Both of those are possible if the sum of the forces on the thing is 0. So it seems like number 1 is kind of like a special case of number 2, but it's not. And it's important that you recognize that what number 1 does is it defines the frames from which we can do physics, that we should do our physics, right? So what I mean by that is, if I get a merry-go-round and I started spinning it, right? I could do a physics problem by, observing the world. I could look at something's acceleration or its sort of position. I can predict it, whatever you like. And I can also stand on the merry-go-round while it's going around and do some kind of prediction. But if I do the latter, I'm going to find some things that are weird. I'm going to find some things that seem like there are forces that are coming out of nowhere, and those are referred to generally as centripetal forces, or more generally speaking, frame-dependent forces. Okay. So you'll see when we do centrifugal motion in just a second what that really means. Okay? But we need to do our physics. We need to always do our physics from the standpoint of somebody who is not accelerating. Right? So I can either sit at rest, right, and watch something happen, or I could move with constant velocity and watch something happen. Those are fine. But I cannot get on a merry-go-round and start spinning and then do physics. Okay? I cannot be in free fall and do physics, because I'll start to see things, I'll start to see accelerations that are induced by forces that don't actually appear to be there. Okay? And that'll become more clear in just a minute. And the last one is Newton's third law, is if I have a force acting between two bodies or two objects, 1 and 2, then F of 1 on 2 is equal to minus F of 2 on 1. So this you should recognize, this is something good that it's good to know. This is the holy grail bread and butter of everything that you ever do. And this one is sort of subtly behind. Do you remember what this allowed us to do? Those of you guys that are in my sections. What did we derive from this part? Yeah, what depended on it? So what was the law that that's right. Conservation of momentum depends fundamentally on this principle. This is not true, then momentum is not conserved. It is a fact that appears to be true thus far, that this is always true, or at least can be written in a particular way to make it essentially true, in the case of the electromagnetic field. But momentum conservation is a very fundamental thing that stems from this idea. Okay. So, let's try this. I have now 2 boxes on a frictionless surface connected by a string. And I pull them with a force. So, the first box has mass 2 kilograms. This has mass 8 kilograms. Okay. And I pull the whole thing with a force of 20 newtons. Notice, by the way, I haven't asked you a question yet. So you shouldn't think that, well, let's see. A lot of times you get the idea that we present you with the situation and they say, therefore, now solve. But I haven't asked you to solve. Okay, so if I do want you to solve for something, what will it be? It will be that I want to know what the acceleration of this system is going to be. Okay? So there are 2 ways that I can do this. But we'll do the more basic way first, and then we'll show how that immediately gives you the more subtle way. Okay? The more basic way requires you to understand what this thing is. Right? What is the string connecting them? I'm giving you the condition that the string can't stretch, nor can it break, and it is always going to be taut, so it's not going to be loose. If that's the case, what does that mean? Does that mean that the force on these 2 guys is the same? What do you think? If I connect these with a string, does it mean that the force on this is the same as the force on this? No, it does not. What does it mean? It's very simple, right? But what does it mean when I connect them with a string?
It means that the 2 masses can be treated as one mass?
Yes, we'll get to that in a second. But more basic.
The acceleration is the same.
Yeah, so they have to move together, right? That's all it means. That the acceleration of this one can't be greater or less than this one, because otherwise either the string would break or it would start to get loose, right? It would start to droop. But I'm saying neither of those things can happen, so the accelerations must be the same. That means the forces can't be the same, because that. If their accelerations are the same and their masses are not, then the forces certainly are not. But, so we'll see what we do. So, we say, all right, let's sum the masses on 1. So, the sum of the forces on mass 1, and this is on mass 1. This is mass 1. So, the sum of the forces on mass 1 are, well, there's some kind of tension force here, T, which I don't know. It's also here. It's acting on both of them. And that's all. So the sum of the forces on this guy is just that tension force, and that's equal to 2 times A. The sum of the forces on 2 is 20 minus T, and that's equal to 8A. And both of these equations must simultaneously be true. So, to solve them, I need to eliminate. I have 2 equations, I have 2 things I don't know. I don't know the tension, I don't know the acceleration. So we'll eliminate one. The simplest thing to do is just add these things together, and what you'll see is on the left-hand side, I get 20 minus T plus T equals 2A plus 8A, or 20 is equal to 10A, therefore A is equal to 2 meters per second squared. to 2 times A. So the tension is equal to 4 newtons. All right, so I found the acceleration, I found the tension. But, as mentioned, when we're doing this, you'll notice that it sort of collapsed. Right? The t that we didn't know canceled with the t I didn't know. And so in that spirit of collapse, what really we're doing with this equation is this is the equivalent of treating these things as one mass altogether, right? Which we're perfectly able to do if their accelerations are the same. If they are always moving, if they're not moving relative to one another ever, which is the condition that we place on it, what that means is just they're essentially just one object. And so you can just treat this whole thing as a case that looks like this. 10 kilograms being pulled with 20 newtons. And now the answer is immediately clear. You don't need to do anything. Right? 10 kilograms being pulled with 20 newtons. 20 over 10 is 2. Acceleration is 2. Okay? Meters per second squared. So this and this are fundamentally the same when you're calculating A. Obviously, you can't calculate T from this problem because there isn't a tension in this. Right? You would need to go back here in order to figure out what the tension was. But purely in terms of mathematical simplicity, if you just wanted to know the acceleration of the system, you can just treat this as one object with mass 10 kilograms, and it becomes immediately clear. Okay? So, something to remember, right? Tension is the thing that ensures the accelerations are the same. In the case of a pulley, it's going to be different because the accelerations are going to be the same in magnitude, but they're going to be opposite in direction. So that'll be something that we'll hit in just one second. I wanted to ask you one more question about this sort of system. Okay, so if I have, blue again. 1 kilogram, connected to 4 kilograms, connected to 5 kilograms. So right now, what's the acceleration of this system? Shout it. Give yourself. 8, right? 1 plus 4 plus 5 is 10. 10 being pulled with 80 gives you 8. Right? 10 kilograms being pulled with 80 newtons gives you acceleration of 8 meters per second squared. Fine. Let me ask you this. If I call this T1, and I call this T2, and I call this T3, which one's bigger? Which one's biggest?
T3.
Which one's smallest? Why?
T1's only dragging 1 kilogram.
T1 is dragging 1 kilogram. T1 is inducing an acceleration of 8 meters per second. All of these tensions are inducing an acceleration of 8 meters per second squared on everything that they're dragging. Right? So this guy has to pull 10 kilograms at 8 meters per second squared. This guy only has to do 5, this guy only has to do 1. Right? So this guy is going to be, this is 10, this is 5, so this guy is going to be twice as large as this. And this is going to be 5 times as large as this. So remember, the tension is the thing that keeps the accelerations the same. Okay? We'll try and expedite, but again. Alright, so I'm not going to do pulleys. Pulleys are essentially this, just looped over a thing, right? So if you can unwind the pulley, so instead of being over a thing like this, you just put it in here, it's essentially the same problem. If you have issues with pulleys, then you can certainly ask me about it, or you can work through your book or extra problems or stuff like that. But in the interest of getting to the things that are actually difficult, I'm going to I think I'm going to lose the pulleys. So I'm going to do 2 things two more chunks. Okay. The first chunk is like an incline with friction, and the second is centripetal motion. And after that, I think we can call it a day for tonight, because we're getting, I think, to the point of diminishing returns, which is always difficult. But okay. All right. So something to recall about friction. So we have two forms of dry friction, which is to say we have two forms of friction from two solid objects coming in contact with one another. We have that static friction and the kinetic friction. So, kinetic friction first. Kinetic friction. I will denote a little f and some k is equal to mu k times the normal force, which I'll denote by that. Okay. So, when you have a normal force, which is the force that's keeping the object from falling through the surface it's sitting on, right? So whether it be an incline or a table or something like that, the normal force is whatever you have to sprinkle onto the problem to ensure that the thing doesn't fall through. But that normal force is something that you calculate last. So you don't say the normal force is equal to mg, or the normal force is equal to mg cosine theta or anything like that, until you've added up all the rest of the forces. Right? And only then can you calculate what the normal force is. This is for the kinetic friction. What about for static friction? So is this, strictly speaking, correct? Of course, I already asked if it was. What is wrong about it? Could be less than that, right? So that is the strictly correct way to write it, but me personally, I like to use this. I say the static max is equal to mu static times normal force, and then at the end of the day, I can, put in my less than or equal to or greater than or equal to something if I feel like it. Okay, so that's my personal preference, but you have to recognize that this is a maximum and not the value at any given time. Okay. Which one's bigger, static or kinetic? Generally speaking, static is larger than kinetic. So we have almost as a universal truth that mu static is greater than mu kinetic. Anything else? Anything else? Okay, so we'll do the incline, and then we'll do the centripetal force, and then we'll get out of here. So, incline. So it's inclined at an angle theta. This is 90 degrees. I have a box. The gravitational force acting on it is straight down, right? And that's mg. That's what has m. But I need to break it up into components. So I break it up into a component that's going into the block, and a component that's coming down the block. So, this angle then is equal to theta. This theta and this theta are exactly the same. If you remember how to do that, or if you don't remember how to do it, try and figure it out. If you do, make sure you know how to do it. Make sure you understand why, geometrically speaking, this theta and this theta are going to be the same. Once you've done that, then you can break this up. So this, the component that goes down the surface of the incline, is mg times the sine of the angle, theta, and this guy is mg times the cosine of the angle, theta. And so I want to know, here's my question at the end of the day. That's the length of my incline. I'm going to say L is equal to, where am I? L is equal to 10 meters. So it needs to slide down at 10 meter incline, by which I mean this distance is 10 meters. Okay. The mass of the thing is 1 kilogram. The coefficient of kinetic friction is equal to 0.1, very smooth. And the inclination angle theta is equal to 60 degrees. My question for you is, how fast will this object be moving by the time it gets to the bottom? So what do we need to do? Obviously, the key to this is finding the acceleration, because once we found the acceleration, we can use our one-dimensional equations to get to what the final velocity is going to be. But to find the acceleration, we need to find the forces. So we need to resort back to Newton's second law, which I've erased. And so his law says that the sum of the forces, and these are the forces that are going to be down the incline, so I'll denote that here. The sum of the forces down the incline is equal to the mass of the thing times its acceleration, and the sum of the forces into the incline or away from it is equal to 0. Right? And the reason that is because it's obviously not moving that way, nor is it moving that way. Right? All this way, which means that the forces in this direction must cancel each other. So we'll see how far we can get with this. The sum of the forces that are working perpendicular, parallel to the space of the incline, I'll define down to be positive. So the sum of these forces, sum of F parallel, is equal to, we're going to have the gravitational force acting down, which is mg sine theta. And then we're going to have a frictional force that's trying to hold it back up, which is that F kinetic. I know, however, that this is equal to mg sine theta minus mu kinetic times the normal force. But here's where I have to stop for the moment, because I don't know what the normal force is. But this is equal to ma. So now let's use this to try and find what the normal force is. So from this equation, you have the normal force acting out minus what force pulling in? mg cosine theta. That's it. Right? And this is, of course, equal to 0, which immediately leads me to this. That the normal force is equal to mg cosine theta. If I were holding this block like that, it would not be mg cosine theta anymore. Okay? If in any way this situation were different, if I were pushing on it, if I were pulling on it, if there was a guy riding on it, if it was being pushed down the incline, if it was being pushed up the incline, it would not be necessarily mg cosine theta. Right? So it's important that you don't just memorize that as the normal force. If you have no other guess, that's a reasonable guess, right? But if you're really, in the midst of solving a problem, don't make the mistake of assuming mg cosine theta is going to be your normal force until you've explicitly found it out. So I can plug that in. So taking this equation, writing it down here, and including that for normal force, I get that mg sine theta minus mu k mg cosine theta is equal to ma. And so I can cancel my m's, which are irrelevant, and I find that a is equal to g times sine theta minus mu k cosine theta. And therefore, v final squared is equal to v naught squared, which is 1, or which is 0, is 2 g l sine theta minus mu. Okay. All right. So that would be the answer if I plugged it into my one-dimensional. If I plug these numbers into this, then I get that v final is approximately equal to 12.8 meters per second. So that's something that you should check. All of these exercises I'm sort of flying through, but you should do them yourself and check to make sure I'm right. That might be wrong. Maybe I'm boo-boo. Okay, but I think that's good. Question though, real quick. Is it worrisome that we have a squared is equal to something with a subtraction bit in it? Right? Because it's entirely possible, to me at least, right off the bat, that this might be bigger than this. Why not? I haven't said anything about what mu k is. I mean, I did in this problem, but I could stand in front of the values here and just say this is the problem, solved symbolically. And I could say, well, I didn't say anything about what this is, right? So for reasonable values of theta, I could just artificially make this larger than this one, which would make this negative. So squared is equal to a negative. That doesn't make any sense, right? So there must be a reason that that's not possible. And so I know I mentioned this to the guys in my section, right? So if you've done this before, do it again. If you haven't done it before, demonstrate why this can never, ever be negative. The reason, and then I'll let you do that yourself, the reason that this can never be negative stems from the fact that mu k is always less than mu static, and it would not have started sliding. So basically what you try and find is, what are the conditions such that when I let it go, it starts to slide? You'll find that mu static can't be larger than a particular value. Otherwise, it will just stay and it won't start to move. So by assuming it starts to move, we have made an assumption about mu static. And by that reasoning, we have made an assumption about what mu kinetic is, because mu kinetic is always less than mu static. So we're giving this an upper maximum by saying that the thing started to slide when you let it go. And so that means this is bounded as well. And what you'll find is that this can never be less than 0. But I seriously urge you to do that by yourself, because this is a very illustrative example. All right, so the last thing that I'll do quickly is that circular motion. And so the way I'll do the circular motion is I'll just introduce it while doing the problem. But I'm going to try and interject this one more time as we do it as well. So circular motion. Something from Newton's first law and from his second law that needs to be just pounded into your brain if it's not already. Okay? And that is, if an object is not moving in a straight line at constant speed, you can either have an object that's sitting still, completely at rest, or something that's moving in a straight line at constant speed. If you have anything other than those two cases, there is a net force on the thing because it is accelerating. It doesn't matter if its speed is changing or not, but its direction may be changing, its speed may be changing, both may be changing, right? But if it's not either at rest or moving in a perfectly straight line with perfectly constant velocity, then there is a net force on the thing. Furthermore, if it's moving in a circle, a special case of it's moving in a circle with constant speed, so its speed is v, the radius of the circle is r. If a mass is moving with speed v in a circle of radius r, and there is a net force on it, that net force is equal in magnitude to mv squared over r, which is also equal to m theta dot squared times r, if you remember our definitions for some of these things. There is a net force on it. If it's not moving in a perfectly straight line at constant velocity, there is a net force on it. In the case that it's moving in a circle, that net force is equal to this in magnitude and is always pointing towards the center of the circle. Okay? One more time. If it's not either at rest or moving in a perfectly straight line at constant speed, there is a net force on it. And if it happens to be moving in a circle of radius r at speed v, then the magnitude of that force, you know what it is. It is mv squared over r, or m theta dot squared times r, whichever you prefer, in magnitude. And it's always pointing towards the center of the circle. So I have two problems that are going to illustrate this principle. The first is, if I have, have any of you guys ever been on one of those like sketchy carnival rides that is in New Jersey? It's called a gravitron.
Yeah.
You been on those things? Oh man, I had a bad experience with the gravitron once. I ate orange chicken beforehand. Yeah, poor choice. Anyway, so You get the principle. For those of you who are unfamiliar with this, everyone goes in, you stand up against the wall like this, and it starts to rotate, right? And so you start to feel like you're getting kind of pushed against the wall, and it goes faster and faster and faster, and then the floor drops out, and you're just being pressed to the wall, but somehow you're not falling down. Right? So my question is, how does this work? So, we're going to have people, poor, sad, throw-uppy people, that are being squished to the walls of this thing. Okay? And it's rotating, I'll make this a little bit more clear. So it's rotating around this way with some speed, some angular speed, theta dot. Which is to say, if theta dot were 2 pi, then it would be 2 pi radians per second. It would be going through 1 full revolution in 1 second. Okay? So, I'm going to say, all right, I am an 800 Newton individual, which means I have 80, that's not that bad. I don't think it's wrong. Yeah, 80 kilograms, right? So I'm 80 kilograms. I'm a little bit more than 80. Weight loss. Okay. This is my mass, 80 kilograms, all right? And let's say the walls of this thing have coefficient of friction, of static friction, mu static, equal to 0.5. All right? And my question is, oh, and one more thing, and the radius of this room, this radial distance, which I'll call r, is equal to, let's say, 5 meters. Okay. So the question is, how fast, in terms of theta dot, so radians per second, how fast does this have to be going so I don't fall when it drops the floor out from under me? So what we'll look at is sort of a cross section. So here is me being pushed up against the wall like that. And so we have a room that's rotating. I'm rotating along with it. As such, I feel a force being pushed out against me, right? I feel like I'm being pressed to the wall, but I'm not being pressed this way. I'm not getting pushed against the wall by a force. The wall is pushing me. The reason I feel like there's a force on me is because I'm silly and I'm trying to do physics in an accelerating reference frame, in a frame that is not one that has been specified by Newton's first law, as we voted up there, right? And so I'm trying to do physics, but there are these forces that I don't know, and they're coming from anywhere they feel